Okay, so like I said, today we're going to talk about the numerical approaches to solving the Schrodinger equation. What do we mean by numerical methods? How to do integration in a spreadsheet, and we're going to do a Kahoot on that and review some terms like fundamental and hot band and those kinds of things. Also, I'll show you the finished product of the spreadsheet that you're building, that you'll have in the lab, and really kind of get you to focus on not just building the spreadsheet, but actually using it to see what happens in the spectrum when you have a change in mass or a change in size of the system, like the box length. Or you can even have some fun and like change the physical constants of the universe by changing Planck's constant and see what happens. So when you have a dynamic system like this that's being modeled, you can open the hood and start pulling hoses and turning screws and see what happens. So yeah, it's much of a pain to do that analytically, by doing the full integrals. But it's much easier when you've got a computer that's faster than you are. It's waiting on you to do something, and you change the mass and it instantly reacts. So it's pretty cool. So let's get started. So we have this wave function that we see on the left, and it looks like our first 4 wave functions. Now they're not spaced up like we've been showing them in the past by their energies. They're all just like a guitar string, and you see the different harmonics. And they're standing waves. That's what we're talking about in terms of a wave function. Let's focus on that blue one there. That is the ground state wave function. So n equals 1 for the particle in a box. And if you stick that in an electric field, we're going to model that electric field with the x-axis, because the x-axis has a positive side and a negative side. So it's as if we stuck this ground state wave function in an electric field. Now the wave function models a charged particle. So the charge interacts with that electric field and it changes or perturbs, that's the word we use, it perturbs the wave function. So on the right we have the perturbed wave function. So we stuck that even function in an electric field which was odd, and the result is an odd function you see on the right. So this dark blue line, the ground state wave function here, was even, and then we multiplied it by x, and x was odd, and so we had even times odd, and we end up with this odd function here. So this is our perturbed wave function x psi. So x times psi is being plotted on the right. And you'll see some of those same plots in your spreadsheet. So in our Schrodinger equation, or our transition dipole moment integral, we're taking the integral over all space of the wave function times light times the initial wave function. And so what we're plotting here is just this first piece. So then we're going to take the wave functions that we have and multiply it by the results of this multiplication. And so we're dealing with, every one of these wave functions is a column in your spreadsheet, and it's 100 rows long. And so we have an array of 100 numbers. And then we have 15 quantum states. And so we have a block of 15 by 100. So that's a matrix. And so it helps us to think about manipulating all of these different blocks of numbers, these arrays, if we can learn a little bit about matrix multiplication and how to manipulate matrices. And so in this transition dipole moment integral, we know that this is reviewed. The intensity is proportional to the result of this integral squared. And then also you have the Boltzmann distribution. Now the Boltzmann distribution is the thermal population of that initial state. If it's absorption, it's the lower state. But if it's emission, it's the upper state. And so if you don't have atoms or molecules or electrons in an excited state, they can't spit out light and drop down. Okay? And so it just depends on the experiment that you're doing of which one we use the Boltzmann distribution on. So for our experiment in the spreadsheet, we're doing absorption. And so this is the Boltzmann distribution, the Boltzmann factor for the lower state quantum numbers. And so let's talk about this transition dipole moment integral, doing it in Excel. We have that perturbed wave function, x times psi. And then we have the state we're going to, so psi 2. That's not very high amplitude, but that's what it is. once we multiplied that ground state by x, it got pretty big. And then we have this second excited state n equals 2 wave function, the green one. And then I've got these two multiplied by each other. So this is the wave function of this product, or the plot of this product, all three things multiplied by each other. And that's this gold line here. And then the integral of this squared is going to be shown on this alternate axis over here. It goes from 0 to 1400. And so what is the integral? That funny shape, this thing here, is really an S, and that's to indicate sum. Thanks, John. So it's a sum. All we have to do in Excel is just sum that column. Okay, now we can put the sum down at the bottom or at the top. What I've done to plot this is I've just put it beside it, and I've said sum this next number and every number above it. And so then the next row is, it adds one more number to that sum, and then the next row adds one more number to that sum. And so I just plotted that column, and that's this red line here. So notice it's not adding very much. Oh, and it's squared too, so that's why everything's positive. So these numbers are negative. So that integral would be negative, but then we squared it, so then it becomes positive. So adding those together and squaring them, that's what we see here. And you see where there's lots of area under the curve, it rises steeply. And then when there's really no area being added to the integral, it flattens out. And then when there's lots of area, it's steep again. Now, why is it steeper here than here? Because we're squaring it, so we're squaring a bigger number. And so it grows fast. And then it reaches this point where the integral over all space for the transition from 1 to 2 with light squared is 1300, like 1298. Okay. So that's our number. That is the transition dipole moment integral result. It's a single number. Okay, and that's the probability that that transition can occur. Now, if we have that times the Boltzmann factor, we have the population piece and the probability piece, and that will be the relative intensity of our peak. So this is what feeds into our spectrum. This is the y-axis of our spectrum. How strong are each individual peaks? Let's look at now 1 to 3. So what's the delta n for a transition of 1 to 3? 2, right? 3 minus 1 is 2. Is that going to be allowed or not? No, it's an even jump. And so we learned from the analytical solutions that this should not be an allowed transition. So we have our x psi 1, that's our perturbed wave function. And then we have psi 3 plotted here, it's the green one. It goes up, down, up. It has 2 nodes, 3 lobes. Here's the multiplication of these two functions by each other in this gold color. Okay. And then we have the integral. And so even though in between, in the intermediate sums, there's some non-zero character, it cancels itself out and goes back to 0. And so when we get to the end, we've summed over all space, and the result of that integral is 0. So that's why I really like numerical calculus, because it's so visual. And all you do is use the mouse and copy things down. You've got your calculus done. You know, it's fantastic. So, all right, let's look at 1 to 4. Okay, so should that one be allowed or not? Yeah, so 4 minus 1 is 3. That's a delta n of plus 3. So that should be allowed. So here was x psi. The green one is psi 4. Here's the multiplication of all three of those functions together. Psi 4 times x times psi. And then we'll integrate over all space. And it bounces around and ends up at 8. Okay, so it is allowed. It's non-zero. It's just not very much compared to 1300. But now what's the term for this? Is it a fundamental, an overtone, a hot band? Overtone, exactly. So it jumps multiple levels, that would be an overtone. Okay, so let's talk about arrays. How are we manipulating these functions to get these various plots? This is new material. I added it last night. So just sit back, take your notes. Okay, there's not a lot on each slide, so you'll be able to copy it down. You don't have to really copy this page down. It's just introducing the concept of arrays. So what is an array? It's just a list of numbers. So, you know, we're going to learn about manipulating these arrays and then looking at multiplication of the arrays. And then eventually a table would be a matrix. So using the whole table and manipulating a whole table at once. And then that allows us to do numerical integration. So any row, column, or block of numbers is an array. So you can have a row matrix or you can have a column matrix. And so very simple, you can just have your numbers in a row, you can have your numbers in a column. And you can operate on the whole row or the whole column. One of the things that we can do to manipulate the row is to turn a row into a column or turn a column into a row. And that's called transpose. So let's learn by inspection. If I transpose this row of numbers into a column of numbers, what's actually happening? It's spinning. It's spinning on that first cell. And so that's the pivot point. The diagonal is the pivot point. There's really not a diagonal in a single row of numbers, but that diagonal always starts with that first value. If I transpose the column, it'll become a row. And again, we will be pivoting on that first cell. It might be a little easier to see if this was like a table or a matrix. So if we transpose this matrix, so here's a 3 by 2 matrix, and it becomes a 2 by 3 matrix. And so we're pivoting on that. Notice A and E stay on the diagonal, so that diagonal doesn't change. But things that are below the diagonal become above, and the things that are above become below. So this is the transpose function, and we use this in our spreadsheet. We'll see in a second a sort of a picture of the spreadsheet and what transpose is doing for our wave functions. But we'll see also in a second why we need to use the transpose. Now, to use the transpose function in Excel, when you have this many cells here, if I'm going to take this set of numbers that is sort of a rectangle that's vertical, and I want to turn it into a rectangle that's horizontal, I've got to select all the cells where I want this formula to go. And so I've got to, if I have this, I put in the formula in all 6 of these cells by selecting all 6 cells, the shape that I want it to take. And how do I know that? Well, I look at this and I say, well, this is a 3 by 2. It's going to be 3 columns across and 2 rows down. So I select that whole block and I type in equals transpose and I open parenthesis and I select this whole block that I'm transposing. I close the parenthesis, and then this is the key in Excel. I have to hit Control-Shift-Enter. So that's how you enter an array formula. So I've got the whole array selected. I just type in the formula, and when I hit Control-Shift-Enter, it completes the whole block. It puts that formula in the whole block. So these array formulas are a little different than normal formulas in Excel. You have to enter them. First, you have to select the whole array that's going to be the result, and then you have to hit Control-Shift-Enter to activate that formula. And so this would be the formula in Excel, and it shows up with these curly brackets to inform you. Like if you were to click anywhere in there, it would say, oh, this is part of an array formula. And so that's what those little curly brackets mean. So that means to change it, you're going to have to select that whole block and change it and hit Control-Shift-Enter again. Okay, so let's talk about array multiplication. It rotates and multiplies and adds. So it does a lot of things at once whenever you're multiplying arrays. And so even though mentally you could multiply a column times a column, in terms of matrix multiplication, it really needs to be a row times a column added together. That's the way things work in matrix mathematics. And so we have this row with numbers 1, 2, 3 in it, and this column with numbers A, B, C. And I'm only doing letters and numbers just so that you don't have to do any math in your head. You can visually see what's being multiplied by what. And so I have number 1 multiplied by A, and 2 multiplied by B, and 3 multiplied by C. Let me move my face down here. And so that's what's going on with matrix multiplication, is you have a row times a column, and it's added together to form the result. And so this 1 by 3 row matrix times a 3 by 1 column matrix would yield a 1 by 1 result matrix, or just a single number. And so in Excel, then we have, where's the formula? Sum product. Okay, so we can use the sum product since it gives a single number. We don't have to use Control-Shift-Enter. The nice thing about sum product is it really doesn't care if it's a column or a row. But if we were to use MMULT, which we'll use next, then it has to be row and column. You have to take care of those things. Yes.
Are we going to have to write like an Excel formula by hand for the test? Or?
No, not really. It's just giving you information about your lab. You're going to have to answer questions about the numerical integration, though. Okay. Yeah. And you may have to do like something simple like that by hand, just so that I can tell that you've captured the idea of matrix multiplication. Okay. So if I gave that problem to you with numbers in all 6 places, could you calculate the result? You know, and that should be straightforward. Yeah. My battery's dead. Okay, here we go. So the nice thing about this is that the sum of an array is an integral. So if we have a way to multiply these values together in matrix format, then at the end, the sum is done for us. And so this is a way to do numerical integration. It's a way to sum columns, especially columns that are multiplied by other columns. So let's talk about matrix multiplication. It's sort of an expanded form of this sum product idea. So if I have this matrix on the left with all 6 of those numbers times this rectangular vertical matrix, what do we end up with? This is our result. Look what's happening here. So we take the top row of this matrix here, and it's rotated and multiplied by the first column, and then that becomes this first sum. Then we take that same top row, and it just sweeps through this matrix. Then it comes through and grabs this second column, and that becomes the top row, because it was the top row initially, and it becomes the second column value. So the top row yields the top row of both of the numbers in our result. And then as it sweeps through each column, it yields the different columns of numbers in our result. Then the second row comes through, 4, 5, 6, and then it is multiplied by the first column and gives us the second row, first column number. And then it sweeps through the second column and gives us the second row, second column number. So that's matrix multiplication. And it can just be expanded. In fact, what we're going to have is a 15 by 100 matrix. It's a lot of numbers. Okay. So we're going to take 1,500 numbers and multiply them by 1,500 other numbers and sum them. And it's going to take the time it takes you to take Control, Shift, Enter, and let go of the keyboard. And it's done. Yes.
So in this case, we don't get a number, we get another matrix?
Yes, you get another matrix. And it's a different shape. Even though this bottom matrix looks bigger than the other two, it's really smaller. It's just 4 numbers.
2 by 2.
Yeah, it's a 2 by 2. So we started out with a 2 by 3, and we multiplied by a 3 by 2, and we end up with a 2 by 2. So you might see, and so here's how you do this in Excel. It's the MMULT function. And array number 1 is the 1, 2, 3, 4, 5, 6 matrix. Array number 2 is the A, B, C, D, E, F matrix. And so then that's how you set this up. So this matrix multiplication rule is something that we need to follow, or Excel is going to give us an error. And we're not going to actually be able to calculate it unless you obey this rule. Because you need to have the right numbers correspond to each other so you can do the multiplication. So we talk about matrices, we talk about rows first and then columns. And so if you'll notice back here, I was talking about a 2 by 3 matrix is the first one. And when I say 2 by 3, that tells me it's horizontally rectangular. It's 2 by 3. And then the next one's a 3 by 2. That tells me it's 3 down and 2 across. So we always talk about row first, then column. And so in these matrices, we have row 1 by column 1 times row 2 by column 2. And these interior numbers must match. So this right here, I've marked in the same color because the columns of matrix 1 have to match the rows of matrix 2 because they're going to rotate and multiply through. And so when you rotate those columns and start multiplying through, then they have the same number of values. And so this is an example. We had a 2 by 3 multiplied by a 3 by 2, and the middle numbers are 3. So that's compatible. Okay. And then the result are the outer two numbers. The rows from number 1 and the columns from number 2 become the row by column in the result. So it's nice to see it all color-coded. You can see the multiplication rule. Now, how do you need to know this? Well, in Excel, this is going to tell you here how big your block is. So if I'm going to do this matrix multiplication in Excel, how many cells do I select? Right? If you don't select the right number of cells, it won't work. Okay. And if you need some more practice on this, the Excel Bootcamp on the YouTube channel has a thing on MMULT, and you can try it yourself, and so it's got some examples. Okay, so you can go back and look through that as well. And so the columns of M1 must equal the rows of M2, and then the result, M3 will have the rows from M1 and the columns from M2. And so once you select that 2 by 2 matrix, then you can say equals MMULT, and then select M1, comma, select matrix 2, close parenthesis, Control Shift Enter, and then the 2 by 2 matrix will have the result in it, and it'll be done. And so in our spreadsheet, we have this enormous set of data, 15 quantum states and 100 rows. Now remember, it goes a little bit past the top and bottom. It goes to 101 and then 102. But whenever our box length is got 100 divisions in it. And so we're always picking from L/2 to minus L/2. And those extra values are really just so we could take the derivative and not break symmetry. Okay, your TA should talk to you about that. If you have questions, we can talk about some more. But you select that 15 by 100 matrix, but it's a vertical matrix. It's a 100 by 15, and we want to flip that. So we want to transpose that so it's compatible with that block of numbers again. So this is the formula that we're using in Excel. We're transposing that wave function block so that it looks sideways like this. And then we're multiplying it by that wave function block multiplied by x. So we have x psi here. So this is, let me change to red. I'll put a little T in a circle up here to show this is the transpose of psi. So we're transposing psi, and then we're multiplying it by x psi. And then we select, before we start that, we select this 15 by 15 block because we know that's what the result is going to be. And so once we select the 15 by 15 block, we type in MMULT, open parentheses, transpose, open parentheses, then we go select that psi block, and then we hit comma, then we select with the mouse the x psi block, close parenthesis, and then we Control Shift Enter, we get this. And we've done 225 integrals. That's great. Think of how long it took you to do one in your Calculus Week lab, right? How many pages? You know, who's got the record for number of pages? You write big. What are some numbers? How many pages was that transition dipole moment calculus? 5? 8? 8 pages? 16 pages? I think you win. 14? Yeah, so, you know, depending on how big your handwriting is, you know, it could be 14 pages and you've done one integral. Now, Excel, we've got 3 sheets of wave functions and so on here, and 15 by 15 block on a different sheet, but we hit Control Shift Enter and we did 225 integrals. The nice thing about that, though, is it's all dynamic. These are formulas. And so I go in and change the mass, and all the integral values shift. I change the temperature, all the values shift. I change all of these fundamental values, and the spreadsheet reacts. So that's what's nice about it. So let's look into this pattern that we see. Do you see the pattern? I mean, I've kind of helped by doing some conditional formatting. If it's below like 0.0001, I said make it gray so that the non-zero values really jump out at you. And so what is this number shown there? That is 1 to 2, okay? And it actually matches 2 to 1 as well. What about this number here? This is 4 to 5. So those are essentially the same type of transition. It's a delta n equals plus 1. Okay. Here's 3 to 3. That's a 0. Okay. 6 to 6 is 0. And so these integrals are 0 when we have delta n equals 0 or plus or minus 2. So here's a plus or minus 2 here. Let's go from 2 to 4. If we went 2 to 6, that'd be a plus or minus 4. It's a 0. 2 to 8, plus or minus 6, that's a 0. And so we see this pattern, the integrals are 0 whenever we're jumping an even number of levels. The integrals are non-zero when we're jumping an odd number of levels. I've shown in green the plus or minus 1s. There's some 5s here. Okay, so this whole diagonal right here is the change in quantum number of plus 3. And this diagonal is plus or minus 5. This diagonal is plus or minus 7, 9, 11. So all of those odd values. Now you say those look like 0 up there. Well, they're just like 0.001. And I've got, so that the numbers are actually readable, I've cropped it at 1 decimal place. So these non-zero patterns are our selection rules. So we can do this numerically. We could have done it analytically and come up with the selection rules. That's great. We can do it numerically. For the particle in a box, it's really pretty easy. I mean, yeah, 8 pages of math, 16 pages of math. It's still pretty easy, though, to come up with the selection rules. It's one dimension. But when we get to atomic spectra, not even molecular spectra, once you get 2 electrons, you can't do it analytically. So there is no analytical solution for helium. That's just helium. We can do hydrogen. There's an analytical solution. We can do the actual integrals for hydrogen. But once we get 2 electrons, we can't do it. And so for helium and above, we don't have analytical solutions. So this is the only way we can get the selection rules for the atomic spectra. And then you put atoms together and you've got molecular orbitals. We don't have analytical solutions for molecular orbitals either. So we have to do those things numerically. And so these are the results of all the different transitions for the first 4 levels and their intensities. And we've seen this plot before. So we're looking at the ones that jump. If they skip a level, if it's delta n equals 2, that's an integral result of 0. If they jump, delta n equals 3, then it's non-zero and it's small. Like I said, 8 versus 1300. So single jumps are more probable than overtone jumps. And then if we're starting in, say, level number 2, so this one would be the fundamental. And this one would be a hot band. This one and this one. Okay. And then this one is called an overtone, because it's jumping 3 levels, starting in the ground state. That would be the first available overtone. Okay. When I say the second overtone, what do you think that means?
5.
Yeah, it's a jump of 5 instead of 3. Okay. You might be confused and think it starts in the second level and goes up to the 4th or 5th. Yeah, from 2 to 5. But that's just the hot band of the first overtone. The first overtone is delta n equals 3. And then if it starts in level 2 and it's still delta n equals 3, that's just the hot band of the first overtone. Okay. And you have to jump 5 levels to be the second overtone. And then you can have hot bands of the second overtone. So starting in 2 and going to, let's see, it would be 1 to 6 would be delta n equals 5. So 2 to 7 would be the hot band of the second overtone. Okay. So these are all spectroscopic terms. We'll do a Kahoot on it here in a minute so that you can test your own knowledge. So that's the y-axis. Then we go back to the transition equation. This was on the first exam. Calculate the transition equation. I think it was for, I don't know, delta n equals 2 or something. This is the fundamental and hot band transition equation, so delta n equals +1. And you get this sort of strange way of writing it. We're kind of keeping this by itself as a constant. You have some proportionality here times that constant, and then you have the quantum number. And so our transition equations will have this kind of feel to them. There'll be a quantum number piece. There's also this piece here that's a lot of times you'll see 0-point energy. Which is this piece right here. And so it will so even when if n were able to go to 0 and the particle in a box, n is not able to go to 0, but in vibrational energy it is. And so if this were the vibrational equation, which it looks very similar to a vibrational equation, v can be equal to 0, and so you still have this extra piece in there, and it's 1/2 times that constant times 2. And so there's this piece we call 0-point energy. You can't get all the way down to 0 in energy. You can just get to the lowest quantum state. But in a confined system, it has some energy that it can't get rid of. So we could do the transition equation for delta n equals ±3. And you see it has similar form. That's why we keep this as a constant, because the proportionality changes, but the constant doesn't change. And so we can fit the overtone series and the fundamental series and hot bands to these different transition equations, and we get multiple measurements of this constant. And this constant is related to the molecule, the atom, in our case, the particle in this box that we're interested in. Because if you think about this, we're not always coming at the system with pure theory and starting from the ground up with the wave function. Maybe we get the spectrum and we don't know it's an electron. And we don't know it's a 7-angstrom box. This constant will tell us all that information. So we fit the spectrum, and then we measure that constant. Every peak is going to give us a measurement of that constant. So if we have 15 peaks, we've got 15 measurements of that constant, and we can get good statistics. So we can have it's this constant plus or minus a small amount because we've measured it 15 times in just taking one spectrum. So isn't that interesting? We can take one spectrum and get 15 measurements of the mass or the box length. And so we can get really good statistics from a spectrum. A lot of times in analytical chemistry, like you're using a spec 20 and you're doing a calibration line, and you're dancing for joy if you get an R² of like 0.99. You know, 2 9s and an 8 would be awesome. With a spec 20, I don't think you could do that. Okay, but with spectroscopic measurements, especially in the carbon monoxide spectrum, we have like 50 to 100 peaks. I think it's more like 25 on each side. So 50 peaks that we measure. So we have 50 measurements of the bond length, 50 measurements of the different molecular parameters. And our fit, if you do the assignment correctly, will be 0.99998. You know, you might get 4 9s, maybe 5 if it's really good. Okay. And so what that means, that R² is a percentage of the scatter in the data that's captured by your model. And so if the scatter in your data is captured by your model to 99.99%, that's pretty good. Okay. And that's what made me want to go into PChem. I was looking at a poster on the wall and my future advisor's, outside his research lab, and I was evaluating where to go for graduate school. And he had this experimental spectrum, and then he had this theoretical spectrum, and they looked exactly the same to me. And I thought, whoa, we can model nature that well? Well, yeah, for small molecules we can. Okay. So that was, but I still was pretty jazzed about that. So I wanted to go do small molecule research, and it was great. And we get 4 or 5 9s in our R². So it's definitely a figure of merit for a geek like me. So this is the spectrum that we just produced. The transition dipole moment integrals are the sticks. The intensities are those values. The x-axis is our transition equation. You've seen this plot before, but I think it helps to go back and always look at these things and make sure you understand them. So here, all of the quantum transitions are labeled. So we have the 1 to 2 here, and that's a very special one. Why is that one special? It's called the fundamental. That's also a special one because it will always be there, even at absolute zero. So if you suck all the energy out of the system, all of the molecules end up in the ground state, and you'll still have the 1 to 2 transition. Okay? The 2 to 3 and above, these are hot bands. So it's excited at the 2 level, and all of these are hot bands. And it would be a really complicated spectrum if our peaks were that close and we didn't have really high resolution. It would just be a blob. Okay? But if we shrink down our spectroscopic parameters, narrow our slits if you're using a scanning instrument, we might be able to resolve those. But if we couldn't resolve them and we wanted to simplify the spectrum, we just cool it down. And if you cool it down, then there are no molecules in the 9th state or the 8th state or the 7th. And so those peaks go to 0 because of the Boltzmann factor. And we could just freeze those modes out, and all the molecules populate the 1 to 2 or the n equals 1 level, and that peak grows in intensity and all those others shrink. We would also always have the first overtone, but it's just so small. You know, it's 8 versus 1300, so it's not going to be very strong. You might be able to see a little bump there. And if it's always in the same position and it's, you know, if you lower the temperature and it grows a little bit, you say, okay, that's a real peak. You know, I'm going to go ahead and mark that, and now I know the energy difference between 1 and 4. If we plot this versus wavelength, then we have a similar plot, but notice how the fundamental is split apart from the rest of the pack. And so that's why a lot of times spectroscopic measurements are done versus wavelength, because it really spreads the data out and gets that fundamental transition to be isolated from the others. You still have the same molecular parameters plotted by wavelength, but it's not as clean. And so a lot of times we will peak pick our values in wavelength, but then we'll convert them to wave numbers or energy to do the analysis, because we actually want this transition equation to do the analysis because it's nice and neat and has that constant by itself. Okay. So let's take a Kahoot. Yeah, back to the long codes. 7007844. Anyone else? Oh, there we go. 3, 2. Oh. Tell me to stop, or I'm going to hit start. Okay. Ready? Okay. Gotta speak up. Okay, so if psi is even, what's the symmetry of x psi? Is it even or odd? Red is even and blue is odd if you're in a back. All right, very good. Because x is odd, so odd times even gives odd. Okay. According to the TDM integral matrix, what are the selection rules for the 1D particle in a box? So we've got this up here. This is really the only one we can see. So see the non-zero cells. So red is plus or minus 1 and 3. Blue is plus or minus 2 and 4. Orange is plus or minus 1, 2, 3, 4, and 5. And green is plus or minus 1 by itself. Yay. Okay, very good. The N equals 1 to 2 transition in the 1D particle in a box is red forbidden, blue an overtone, orange a hot band, and green a fundamental. So the N equals 1 to 2 transition. Yay, very good. I'd like to see that split. Okay. Now in vibration, the lowest quantum state is 0. So it'd be 0 to 1 in vibration. This is particle in a box, so it's different depending on the system. Just making sure you sort of catch that. The N equals 3 to 4 transition in the 1D particle in a box. 3 to 4. The forbidden, an overtone, a hot band, or a fundamental. Two people. Make your choice. Okay. It's a hot band. Pretty good. All right. And why is it not forbidden? Well, nobody said forbidden. Okay. It's 4 minus 3 is 1, so you know it's an allowed transition. Okay. Why does that say X? Okay, the 1 to 4 transition in a 1D particle in a box. Is it forbidden? Is it an overtone? Is it a hot band or a fundamental? You guys are on to me. Yes, 4 minus 1 is 3, so that's our overtone transition, our first overtone. And then 2 to 4 transition in the 1D particle in a box. Red is forbidden, blue is overtone, orange is hot band, and green is fundamental. Everybody's like ready to go. And then there's two people who are like, oh, I just can't. Yeah, they're asleep. Look next to you and see if someone's asleep. Give them that little. Yeah, that's the forbidden because 4 minus 2 is 2. And so, all right, so there's our winners. Yay. All right. I know. You had to be fast today, apparently, because I saw those numbers just flying up.
It's hard to get it.
Yeah. Look at that. Pretty close. What's that? Okay. Now, what's interesting, here's the spreadsheet. So, if you can see that. Here's the final product. So we have the box length, we have the electron mass, we have the temperature. Now, one of the questions is asking what it does for temperature, and you're going to get a messed up result if you ever go to 0, okay? Because in the Boltzmann distribution, where is temperature? It's in the denominator of the exponent, and it's going to blow up the spreadsheet. I mean, what does it blow up look like? Okay, 0, okay? And our spectrum goes away. And so people are like, 0 Kelvin, everything goes away. Well, it doesn't, okay? It goes down to the n equals 1 state, but you're actually giving it an error. Just think of it physically, too. We can never get to 0, okay? So you can go to something close to 0, like 1. Okay? So at 1 Kelvin, there's our fundamental, okay? Everything is frozen out, okay? You might be able to see the one little, there's a peak right there, okay? Our first overtone. It's still got some intensity to it. So 8 and 1300. So let's go back. Let me undo. And undo again. Okay, so the reason we go to such a high temperature is we just want electrons to be up in the excited state so that the spectrum will be interesting, okay? Is this realistic? Well, maybe on the sun, okay? So, but I don't know about confining electrons to 7 angstroms on the sun. But it is that hot, at least. Okay. Fusion reactor. Now, the mass, I could go to a proton, but that's changing the mass by 1,000. And this visible spectrum is now going to be in the deep infrared. Okay, so it'll be confusing because your x-axis is going to jump all over the place. Your wavelengths are going to go from like 100 nanometers down to, 2,000 nanometers. So it'll be confusing. So just change things by a little bit. So instead of 9.1 times 10 to the minus 31, let's just go to, let's just say 9 and see if we can detect the difference. So watch the maximum of this peak. Everybody see that right there where the mouse is? Okay, watch that. Tell me if it goes left or right. And left is short wavelength, so that'd be a blue shift. And right is long wavelength, that'd be a red shift. So blue, red. I'm going to change the mass. What do you think it'll do? If I make the mass smaller. Where's mass in our energy equation? In the bottom denominator. So I'm dividing by a smaller number. Okay. So the energy difference is going to increase. But this is differences of those differences. Okay. And so then the differences of the difference should increase. So let's make it 9 e minus 31. So that's a way to do. Oh, I couldn't detect it. Okay. Okay. So let's go to 8. 8 e minus 31. Okay. It shifted left, so it's blue shift. Small mass, blue shift. Okay. So the smaller the quantum particle, the higher the energy difference, the easier to detect those quantum differences. We can do the same thing with box length. So that's the point I'm trying to get you to. Everybody pay attention. I want you to get to the point where you can play with this. Building it is difficult, I acknowledge that. But once you get it, then play with it. See what the electron mass does to this thing, and see what the length of the box does, and so on. You're able to actually modify the spectrum by changing the fundamental constants of the system. That's cool. It really is. You don't get a chance to do that in any other class where you actually have a realistic spectrum and you get to see what happens if you find an electron in nature that weighs 8 instead of 9. Okay, so it's really very interesting. And I know that it's because I do this for a living, right, that I'm super excited about it. But I'm trying to kind of get some of that to rub off on you. Once you get this really dynamic modeling spreadsheet, play with it and explore it. That's what the discussion and questions are trying to get you to do. Okay.